If you write an equation in logarithmic form, you can translate it into an equation in exponential form, and back and forth. How do you do that? What equation is this the same as? Well, what's the base? What should I raise to the exponent? Something on the other side equals. Cool. So, if you have an equation you want to solve, there's an x inside of the parentheses in the log. There's how to get x on its own. Any log of 1 is? Yeah, but say it louder. I think you're about the right thing. 0, yeah. Log base b of b? 1. If you multiply two things inside of a log, then what is that? Addition outside of the log. Ooh, so maybe I'll give like an exam take or tip. At some point, I'll probably put a multiple choice on an exam in which I have you identify some logarithm laws. And as one of the distractors, I might put something like that. That's a false statement. Log of a sum is not anything special at all. Division inside of a parentheses, what's that the same as? Subtraction. Exponentiation. Yeah.
We can move the y up front, so we can y log dx.
Nice. Cool. So there are like the things you can do to just manipulate how the algebra walks with regard to logarithmic expressions. So one analogy I heard for these from just a colleague when I was a grad student is you should think of a log as doing to operations what his mindset with being a cyclist does to the rules of the road. So when you come to a stop sign as a cyclist, at least these are his words, these are not legal advice and it's wrong, treat that red light like a stop sign. Stop, look both ways, if it's clear you can go, you're a bicycle. If you come to a stop sign, really it's a yield sign for you. Everything goes down a degree. If you're a cyclist, you shouldn't ride like that. That's a good way to get hit. Anyway, he did at some point get hit. He also got knocked off his bike at some point and beaten up and mugged in grad school, but that's a different story. Change your base formula. You have a base in a log that you don't like. How can you rewrite that logarithm with respect to a base that you do like?
Log b of x divided by log b of a.
Nice. And you can choose any base b that you want, and that's a true expression. The most obvious way to use that is if you have a calculator that works base 10, then translate everything to base 10. Now you can plug it into a calculator. But there are other times when there's just a different base that you'd rather use because of how things look. We'll see some examples of that today. Change your base formula for exponentials. You have an exponential a to the x, and you'd like to work with a different base. How do you do that? It's in the list, right? Yeah. So, the change of base formula for exponentials is maybe the lowest priority on the list, but that's not to say it's not an important formula. Concludes that a to the x is the same as your favorite base to the power x at the cost of multiplying by log base b of a. And we saw an example last time where that was important, right? We saw that if you have an equation you want to solve where there are two different bases, you can arrange that they have the same base. You can put both of these. We did do this one last time, right? Okay. Concerned I had my sections swamped again. You could write everything here in terms of base 10. You could rewrite that pi to the x is 10 to the x plus 1 times log base 10 of x. So the equation is now two exponentials, both of which have 10s in the base. Well, 10 to the x is a one-to-one function. So you can just set the exponents equal. That means x plus 1 times log 10 of pi is equal to x. Does that look like an easier equation to solve? Does that look like an equation that you just know how to solve? Basically, I'm asking, should we finish this example right now? Is there a call to do it? Cool, then let's do it. Space off in the margin. All right, so here's how to think about this. That log base 10 of pi is a constant. That constant is like a little bit less than 0.5, I think. So if this instead said x plus 1 times 0.5 equals x, would that be easy to solve? And in order to, I think, see this idea, let's get an idea using that. So what if I asked you to solve this? X plus 1 times 0.5 equals x. If I asked you to solve that, what would you want to do? Let's see, what's annoying is that there's an x on both sides. So you want to get all the x's onto the same side. But there's some parentheses on the left-hand side that stop you from doing that. How can you get rid of those parentheses? Distribute. So let's do that. That becomes x times 0.5. I know 0.5 is a half, but I'm not actually interested in that. All right, what would you want to do next? Well, the thing that's annoying is there are x's on both sides of this equation. How can you get all the x's onto the same side?
Subtract after x.
Yeah, subtract 0.5 times x. You do that, and maybe you do some distributive law stuff on the other side. Factoring. You get this 0.5 is equal to x minus 0.5 x. All right, and let's carry on from there. You want to solve that equation? What seems like a reasonable next step? What's x minus half of an x? It's half an x. 0.5 from this side equals 0.5x. Cool, so what is x? Here's the point. If this 0.5 was some other constant, could you still do this first step? Could you still do the second step? Going from here to there, well, you're not going to wind up with a 0.5 in front of the x if this instead were like a 0.7. You get something else. But the same philosophy holds. So let's follow the same instructions here. You want to solve this. Let's start by using the distributive law. X times log base 10 of pi plus log 10 of pi equals x. Fair enough. To go from here to there, we did some subtraction to put all the x's on the same side. So let's do the exact same. Let's subtract to get all the x's on the same side. what do you get when you change this equation by subtracting to get all the x's on the same side? What are you left with on the left-hand side? Log 10 pi. This is the only thing you're left with on the left-hand side. Log 10 pi. And on the right-hand side you have? Well, you still have this x, right? And what do you subtract onto the other side? Nice. Cool. So that puts us at this step. To go from here to there, we combine those two terms with x's together. We can still do that here, right? We could factor an x out. Log 10 of pi equals x times 1 minus log 10 of pi. All right, by factoring out the x. And what did we do in the very last step in the thing at the top of the page? Well, that's no longer on the page. What did you do to go from this line to that line? You divided, I guess? So let's do the division. What do I want to divide by to get x on its own? The thing next to the x. Yeah, so let's do that. So this means that the solution to this equation is x equals log 10 pi divided by 1 minus log 10 pi. That feel pretty good? And if you want to double check that that answer agrees with what we got that the ballpark should be, maybe bust out your calculator. Is that reasonably close to 1? I guess if you don't want to do that, we don't have to. I'm happy enough. All right, so what else can you do with this change of base formula? One thing you can do is you can use it for graphing. So your calculator only knows about one base for any log or any exponent. It knows about base e. Any other base, it translates. And let's do an example of exactly that. So of these two graphs, one of them is 3 to the x and one of them is 2 to the x. And to figure out which is which, let's try to put everything in terms of the same base. So let's rewrite this 3 to the x with a base of 2. So by the change of base formula, that 3 to the x is the same as 2 to the what power? So the a, I guess, is like the 3. 2 is the base I want. So I'll get 2 raised to the x multiplied by log base 2 of 3. All right, so let's think about this. So it looks like the only difference between 3 to the x and 2 to the x is the x in the exponent is multiplied by a number. What happens to a graph when you multiply the x in the equation by a number? It does something horizontally, right? Opposite. It'll compress. The thing you do directly to the x does the opposite of what you expect. So all the x values will get divided by log base 2 of 3. Log base 2 of 3 is 1.58. So if you wanted to go from y equals 2 to the x to y equals 3 to the x, you compress all the x values. So, with that in mind, one of those is 3 to the x and the other one's 2 to the x. Which one's which? I'll label them as A and B for now. Should A be 3 to the x or 2 to the x? Which one of the two looks like the other one but squeezed towards the x-axis, towards the y-axis? Which one looks like it's horizontally compressed from the other one? B is the compressed one? Nice. So that means that this B is 3 to the x. This A has to be 2 to the x. That feel pretty good? So all exponential functions are the same graph. They're just maybe compressed horizontally some. I think I want to close with this one last example. This one will require some algebraic cleverness and will be relevant to some stuff that's in the homework that's supposed to be challenging. Log base 2 of 3 times log base 3 of 2. Let's try to get an exact expression for that. And like neither of those two things we can compute directly on the notes. I don't know what log base 2 of 3 is or what log base 3 of 2 is. And like I see two different bases involved. That's kind of annoying. Let's rewrite that so there's only one base involved. What base would you like to use? Yeah.
6.
Let's use base 6. Sure. The truth is it won't matter. So let's see what happens. Let's rewrite everything here on base 6. If you want to use a different base, use a different base. So we write log base 2 of 3 using this formula in base 6. So the change of base formula says that this will be log base 6 of something divided by log base 6 of something times, in blue, log base 6 of something divided by log base 6 of something. Right, that's what the change of base formula looks like. So, now you just have to tell me what goes in those parentheses. So when you're at log base 2 of 3 using the change of base formula, what goes in the parentheses on top? 3. The thing in the parentheses goes in the parentheses on top. The thing on the bottom? 2. The base of the log goes in the log on the bottom. Same thing with the thing that I wrote in blue.
2.
And?
3.
All right. So by the change of base formula, this is equal to the thing on the previous line, the thing we started with. Do you see anything that simplifies there? Do you see everything that simplifies there? Yeah, cool. So what are you left with?
1.
Just 1. And like 6, I definitely get it. That's an intuitive choice because like 2 times 3 is 6, right? Was it actually important that I put a 6 in that base? It could have been anything. If anything, like either base 2 or base 3 might have been easier, because then I would have had to use the change of base formula only once. But, you know, who cares? It works. Yeah.
If you were to just change one of them to the other, how would that look like?
Yeah, let's do it. Would you rather see base 2 or base 3?
Do base 2.
Base 2. So the first piece is going to stay the same. It is already base 2, so it will stay base 2. This one will change to base 3, so it'll be log base 2 of 2 divided by log base 2 of 3. All right, see anything that simplifies? Gesundheit. I see those cancel, leaving me with log base 2 of 2, also known as 1. Very nice. Feel pretty good about this? All right. So, what I'd like to do today is just more walk solving algebraic expressions involving logs. And we've already got lots of practice on this. So I'm going to take a moment and put these down in my copy of the notes for completeness. You already have them. B to the y equals x. 0, 1, log x plus log y, log x minus log y. I suppose I'm being a little bit lazy and leaving out the bases. And they do matter, right? I guess I'm trusting that I'll just, if I look back at this, intuitively know that I don't mean base 10 here. Y. You know what? Maybe that means that I just shouldn't do that. Log base a of x is the same as log base b of x. I get to pick b. Divided by log base b a. A to the x is the same as b to the x times log base b of a. Cool. All right. So let's use these to solve some things. Some of them are going to look really familiar. Let's suppose I ask you to solve that equation. That look reasonable to do? In fact, do you just think you could do it in like 2 minutes? Nice. Then, unless there's a call for me to say anything, solve that equation for me. And like talk to each other, right? So, without doing any algebra, I like to instead use a graph to tell me at least a decimal approximation to begin with. I am getting that the solution to this should be that x value of negative, it looks like 1.5 repeating. That looks like it's, what, 1 5/9? So, gosh, 5 plus 9 is 14, so 14/9. That agree with what your algebra says? Cool. Anyone feel like they'd like to see that one talk through it? Nice, then let's do it. So we already did, the graph tells us a prediction for what the answer should be. In fact, if you can recognize fractions from decimal approximations, I even know what the exact value is, I think. But let's try to solve this. So where did people start? So people who got that 14/9 answer, what was your first step? I guess it's got a thing in parentheses telling you what the first step is, right? That's already an equation in logarithmic form. And all the unknowns are inside of the log. Whenever you're in that situation, you want to put that thing into exponential form because then all the x's won't be in a log. If there are x's on both sides of the equation, then you're kind of stuck. Not every equation can be solved algebraically, but this one can. Cool, so let's do that. So the base is 3, raised to the power -1 equals, nice. That look like an easy equation to solve? Yeah, 3 inverse is 1/3. So 3x plus 5 equals 1/3. So, you want to solve that for x? What seems like a good next step? Subtract 5, which is 15/3. So 3x equals 1/3 minus
15 over 3. And maybe some color coding is nice just to see how things are. That 15 over 3 is that 5. So I guess that's negative 14 over 3. Alright, so 3x equals negative 14 over 3. What next? Divide by 3. And if you divide by 3 and divide by 3 again, that's the same as dividing by 9. Cool. So let's carry on. The next two equations, let's see, between 2 and 3, I think I want to talk through go through one or the other, but certainly not both. Do people have a preference between we should talk about 2 or 3? We should talk about 2. One with the LNs? Cool. We should talk about them. Alright, I think it was 2 to 1, but things with natural logarithms. So, we have the same philosophy. Whenever you see an equation that's got a bunch of different logs in it, you can use these logarithm laws to combine the logs together. And I think so maybe with that mindset, maybe we can just rewrite it so all the logs are on the same side. Then we'll see a bunch of multiplication of logs by constants. We can turn those into exponentials. And then we'll see some pluses and some minuses. We can turn those into multiplication or division. That seem like a plan? Let's do it. Those of you who want to do it on your own, as is customary, you will be done long before I am. So, let's see. I think it's reasonable to subtract that to the other side. But let's also do something with this 2 times a log. What could I do with that 2 next to the logarithm?
Put x plus 1 squared.
Yeah, I could put it into the exponent inside of the parentheses. So this will be ln of x plus 1 squared minus ln of x plus 2 minus ln of 2 equals 0. You don't have to move that ln of 2 to the same side, but I think this is a reasonable strategy. I see some subtraction next. What does subtraction outside of the log turn into? Division. So I can rewrite this as a single log now. ln of x plus 1 squared divided by x plus 2, and then I need to divide by 2, equals 0. And I might wind up having to FOIL out that x plus 1 squared at some point, but we'll do it when it becomes apparent whether having this thing factored is helpful or not. All right, what next? Are all of the unknowns now inside of a single log? As soon as all of the unknowns are inside of a single log, rewriting an exponential form is helpful. Because it'll get the unknowns out of that log, and it'll just make the log go away. That seem like a fair game? What do you get when you rewrite that in log? Nope, exponential form. Gosh, well, what's the base? E raised to the power 0 equals. What's on the other side of the equal sign? Nice. And I think someone did whisper this under their breath already, but what is e to the 0? Just 1. So this equation, the e has gone away completely. X plus 1 squared divided by x plus 2 times 2 is equal to 1. Oh, nice. Do we have just a plan of attack for this by default? What should we do?
think cross multiplying is a good start. And as we do that, I think I'm going to wind up, that'll give me like a quadratic equation, right? So I may as well make it so that like I see something that looks like a quadratic equation as I go, so I guess I should FOIL out the numerator and distribute the denominator at the same time as I do this.
X squared plus 2x plus 1, there's the stuff in the numerator, equals 2x plus 4, there's the stuff in the denominator.
We feeling good so far? What should we do next? Yeah. So ln is the natural logarithm. The natural logarithm
Has a preferred base.
ln is called the natural logarithm, but it just means the logarithm with base e. So whenever you see ln, you should think log base e. The reason it gets called the natural logarithm is because its properties from the point of view of calculus are so nice that all of the other logarithms are like slightly parabolic cousins to my left. ln just walks that off. Some mathematicians don't want to keep writing log bases, so they're writing ln. Cool.
So we get to there.
What next? I don't know, it's a quadratic equation, right? Let's just see if anything cancels from both sides, and we'll see if we have to use something so big and heavy as the quadratic formula, or if we can like do something easier. Do you see anything that can't just straight up cancels from both sides? The 2x.
Cool.
So this is a quadratic equation, but there's no linear term anymore. Since there's no linear term, we could use the quadratic formula, but it'll be like overkill. Let's just move everything that's not x to the other side and then take the square root. That'll be easier. So, doing that.
I think I wind up with x equals plus or minus square root of 3.
That agree with you? All right. There's one last step that I should do, and we talked a little bit about the importance of this step last time. What should we still do? Solution set. See if it's actually like a legal solution. Both of these are legal solutions by thinking about domain. So let's think about domain and just see what we decide. I see an x plus 1 in the parentheses. So if I take plus the square root of 3 and add 1 to it, is that still positive? Yeah, positive plus positive. Positive plus a positive is positive. If I take minus root 3 and add 1 to it, is that still positive? No, minus root 3 is like, it's like negative 0.8-ish, right? Negative 1.8-ish. Negative 1.7-ish. The point is when you add 1 to that, it's still negative. So, by glancing at this,
You see negative root 3 is not in the domain. X equals plus root 3 is the only solution.
all right. And you can also see that sort of fact by looking at a calculator, a graph generated by a machine. So, let's do that. I'm going to pull up a bit of Desmos. Let's graph the original equation. 2 times ln of x minus ln of x plus 1. That's one side of the equation. The other one is y equals ln of 2. So by just looking at this graph, how many solutions should there be? Just one. Yeah.
Is that technically correct?
Probably not. What looks wrong?
Should there be 2 ln x plus
Yes. Better now? All right. So the question I still asked, like, the answer stayed the same though, so that's nice. It looks like there should only be one solution, so two solutions can't be right. And this is just me reminding you that even after you find the solutions, you can check using a graph. You can let a computer help you check your answers. This 0.73, I don't know, if you're like really able to recognize numbers, maybe you'll think, I think that's the square root of 3, but I couldn't. Neat. Feel pretty good? So, if you see an equation that's like a bunch of linear stuff combining some logs together, you can solve it. Turn it into a single logarithm using logarithm laws. Put it in exponential form. Job's done. Or, that's a lie. You have to do now algebra, but it's algebra that doesn't involve logs. So, I want to take some time and remind us that all of this stuff about logarithms is inspired by something. The point of logs is that it gives you the things that undo exponentials. And exponentials, those come from all over the place in nature. Anything that has a growth rate that's proportional to its size is an exponential function. Populations grow faster or more than their area, those are exponential. Until they like reach limits on their population. Money in a bank account grows exponentially. The more money you have in the account, the faster it grows. That's an exponential behavior. Radioactive decay is exponential. The bigger a radioactive substance you have, the more of it decays in any given time. So, let's remind ourselves of that formula. Radioactive substances decay at a rate proportional to the amount of the radioactive material. As a consequence, scientists often find it convenient to record the half-life of a radioactive substance. All the half-life is it's the amount of time needed for the material to reduce in size by a factor of 2, to get divided by 2. Sometimes it's also useful to talk about like the quarter life or the 10th life of a substance, which is exactly what it sounds like. It's how long does it take to reduce by a factor of whatever you want. A radioactive material has half-life lambda, which is just often a letter that physicists and chemists like to use to denote half-life. The formula for the amount you have left after that time is initial quantity times 2 raised to the power of time divided by half-life. And we talked about why that formula was sensible. Time divided by half-life gives you how many half-lives have gone by. So you need to divide by 2 that many times. That's the same as multiplying by 2 raised to negative that power. We feeling good? So, let's use this. U-232 has a half-life of 70 years. If I give you a 1 kilogram sample of U-232, how long does it take to decay down to 1 gram? So, let's write down just some equations that model that. So let's see, how long will it take? That tells me that I want to solve for t. I want to know what time. So I want to solve this something for t. I guess that means all the other things should be known already. What's the initial quantity of this radioactive substance? How much of it do I start with? 1 kilogram? And I've got the color, so I may as well use them. Q0 is a 1 kilogram times 2 to the negative. T is the thing that I need to solve for, so it'll be a variable. Do I know the half-life? What's the half-life? 70. Does that pen show up okay, even if you're in the back? Okay. And Q of t is the quantity at any given time. What's the amount that I am waiting for the substance to get down to? 1 gram. Nice. So there was nothing special about what we just did that was like unique to exponential stuff. This is just how do you use a mathematical model. But now that we have the model written down in this particular case, that looked like something you could solve for the unknown variable t. Cool. So maybe I'll advocate for it's better if you do it and then we like check at the end in a few minutes. Does anyone not feel like they know how to get started and want me to say things? Cool. I'll point out that the units don't match. Fix the units fast. Settle down to an answer, maybe I'll point out that this is a very applied sounding problem. So a decimal approximation would probably be appropriate. So perhaps just because I'm down to 2 minutes, let's follow this pattern. So how many people got down to the point where they have an answer that they're reasonably confident in? How long will it take?
697 years.
697 years? Do I hear a second? And in order to check, so that 1,000 comes from the fact that 1 kilogram is 1,000 grams. Yeah, looks like about 697 years. 698, I guess, is how it should be rounded. Because that 0.6 will make it round up. Let's talk through solving this. So a reasonable starting point is let's get everything in terms of grams instead of kilograms. How many grams to a kilogram? 1,000. It's from the Latin. So I'll do that, and then I will suppress the units. All right. So I want to get t on its own. What seems like a good first step?
Divided by 1,000.
Divide by 1,000. Ooh, so I'll point out a common pitfall that I see people make. Order of operation says that only the 2 is being exponentiated there, not the 1,000. That 1,000 is multiplied out after you do the exponentiation. So you have to undo it first. That looks like an equation in exponential form, right? And all the unknowns are in the exponent? Let's put it in log form. What do you get when you do that? What's the base? The thing inside of the parentheses?
0.001.
I agree with that, but I had already written the ones where I didn't want to erase. Same as what you said. What's on the other side? All right. And to get that on its own, what do you need to do? I'll divide by negative 70 to get rid of the negative at the same time. Negative 70 times log base 2 of 0.001 equals t.
So how many people look at that and say, that's weird, that looks like a negative time? Oh, well, that would be perfectly reasonable to be upset by. It looks like it might be negative. But let's know whether it's less than 1 inside of the parentheses. Log base 2 of 1 over 1,000 is negative. So I see negative times negative. It will be positive. And your calculator will also reveal that that's positive. It's like 678.
And if that's where I'm stopping, I better indicate the units.
Cool. Anyone planning on coming by my office during my 1 o'clock office hour to maybe talk about things about that exam? Cool. You'll notice that I entered grades for the points back thing. That doesn't mean the points back thing is closed. I just wanted to give you an idea of where you stood right now in case you wanted to make another attempt. The deadline for that, I think, is tonight. What was your grade? Was your grade on the actual exam more than 90%?
Yeah.
Yeah, then since you already had an A, I decided you didn't need it. So that's the rule that I stand by. Like the points back, there's an incentive to make you study. Hopefully it was useful to you.
Yeah.
But if you want to get like, if you want to improve past an A, you had to have gotten it right on the posture. Yeah. And I think it was like you fell into the pitfall that, if I remember right, you like got one of the multiple choices wrong, and you like didn't show enough support or something.
No, I got like almost correct, and then I got one answer that I really think that is correct. No, but
That will get you points back if you come back to the office and tell me about it, because that would count as you playing an error and no one else is playing out.
okay.
So come by my office sometime and explain to me the thing you did is wrong. I'll know you. Yeah.
I can't remember your office hour, but I can just this. I just put it in a different way. Instead of doing a minus sign, it just makes more sense to do subtraction and subtraction. And I'm pretty sure like the answer that I got was right.
Oh, it's not.
Oh, it's not?
Yeah, and that's, so since you did distribute the minus sign, which, oh! No, your problem isn't you didn't distribute the minus sign, you didn't write down the problem correctly. That should be a minus, not a plus. Yeah, okay, so my diagnosis of the error was wrong, but like, there's the actual problem.
Okay.
That's not a 2-point error, that's a 1-point error, you copy down. And I will forget all about this.
Oh, I hope we go back like 4th grade.
Email me with a reminder of this conversation, I'll give you a one. But let's see, did you already do the review for points back?
Yeah.
Did you get more than 90% on it? Okay, so your end grade won't go up at, if you want to just like have it corrected there, just because you know the Yeah. Okay. Yeah, so all the lectures get recorded. Let me show you where to find them. So you can